Okay, let's have a class. And today we will talk about the lacto operant. There is a lots of topic we could talk about that. And there is the information is comprehensive. So we want to talk about the detail of it, and there's lots of the material we could using talk about lacto operant, so we can do the review. Okay, so this is usually I talk this at the end of the exam series. The reason is it is comprehensive and it is kind of like a review for you. So first of all, we talk about the central dogma already, and you know that we finished talk about DNA replication, then going to the RNA, which is transcription, and then going to the protein, which is we call it the translation. Now this is a process usually very routine for the bacteria to survive. Lots of the time, bacteria need to biosynthesize. They are I will say it's a very it's a stable structure. For example, peptidoglycan. Then they have to go through this procedure. And there is a certain gene responsible for that. We call it a housekeeping gene. And those genes are very stable. So we don't talk about these too much right here. But most of the time, the bacteria live in the environments. It's going to be changed as the growth situation. So for example, let's say there is a photo. There is a photosynthetic, which means there's a light. This as a sensor. Okay, once you bacteria have these type of, this is a stimulant. We call it a stimulant. Once you have this stimulant, then bacteria will have a cell membrane sensor system to feel about this stimulant. Then later on, what we're going to happen is they're going to do an amplifier. Amplify this sensor. Then they will be related to the gene open and close. This is corresponding to lots of the things we call it a regulation. Then the regulation, obviously there is a two levels of the regulation. If it happens from the DNA go to RNA, this is we call it a transcriptional regulation. If it happens from RNA to protein, we call it a translational regulation. So this is the overall structure. The overall picture, what happened for the gene regulation. Now, what are we going to talk about today is post-transcription regulation, right here, regarding the lacto operant. Okay, so that's something we want to mention, give you the over picture, what thing it is. So let's talk about the lacto operant. Okay, before talk about the lacto operant, we want to give you an overall view what it is talk about the operant. Basically, let's say there is a structure gene. It's like this. We are talking about is three locations. We call it A, P, O. And the downstream here, this is a functional gene. And different functions that could relate to that. Okay, so this is the structure of a structure gene, what it is. What is A? Activator, protein, binding site. What is O? Operator. What is P? Promoter. Now, we already talked about the promoter, so we can do a review. So for bacterial cell, the promoter, what is that? Remember, minus 35 and minus 10. What is minus 35? That is 35 base pair upstream of the initiate place of the transcription. The conservative sequence is called TTGACA. And what is minus 10? That is, we also call it a pyramidal box. And the pyramidal box is about 10 base gene upstream of the initiation, the location of the transcription. That is the TAP. And we say it's a very conservative sequence for the promoter. And what is the function of the promoter? The promoter needs to be combined with the big chunk of the enzyme right here. It is called RNA polymerase. And we can also review the RNA polymerase. It's the two subunits of alpha-2, beta prime, omega, that is, we call it a core enzyme. And then, don't forget, we need a cofactor, which is a sigma factor. And usually we say it's a sigma 70, because the molecular weight, total of sigma 70 is 70,000 delta. So that's why we call it a sigma 70. And this sigma 70 to help the RNA polymerase to recognize the promoter, and then they started to do transcription from 5 prime to 3 prime. Okay, this is something, is the overall picture. We talk about the promoter, we already talked about. Now we want to talk about regulation, okay? So I'm going to draw here again. We have 3 locations. A, P, O. And I said this guy right here is RNA polymerase. Now, we can say very simple. Right here, we cut in the middle. Anything happens on the right side, facing the blackboard, which we call it a downstream, this is negative control. Anything happens on the left side, which is we call it upstream, that is positive control. So, said very simple, negative control is something going to happen on this O position, and the positive control is something happens at the A position. And most of the time, these are enzymes, these are proteins, attach or release, and with some effector. It could be a repressor, it could be an inhibitor. These just some of the examples. So this is the overall picture. Now the negative control and the positive control, we also going to have 2 groups, which is inducible and repressible. Okay, what are those? Before we go over the detail, we want to make sure we have a joke to share with you to understandable. The promoter and the polymerase, RNA polymerase, when they get together, this is very similar, like 2 people are dating, and then they get married, and then they have a baby to have a family. And then you have a pressure from both sides. You can understand the positive control may be some pressure from your parents' side. And the negative control may be some pressure from your in-law side, the mother-in-law and father-in-law. And then you have an inducible and a repressible. That could be something to prompt you to work hard to get a good career. That's repressible, something to limit you to your life. Let's say you don't have a budget to buy a big house. You may have only can buy a condo or a small apartment. And these are the things we also could give you an example. When they started to combine together, the transcription happens, seems like the boy and the girl have a baby when they get married. They want to have a baby. But sometimes the parents will say, okay, go ahead to have it. I want to have a grandson very soon. But on the other side, the mother-in-law and the father-in-law, they maybe say, I don't want it because the boy has promised you something he hasn't done yet. So all these things is back and forth to control, they'll get together to have transcription. And it is same for the bacteria. It's happening in our lifetime all the time for everybody. And this is same for the bacteria in their short lifetime. There is a difference from left, from right, from different level to control. They combine together with RNA polymerase and the promoter to have a transcription. And further down is a translation. Okay, so just share your joke and just you understanding these things, how it works. Now we want to talk about these details. First of all, let's try it again. What is called negative control? What is really called positive control? We try it again. Okay, let's say we have A, P, O, 3 positions. So we draw these two right here. A, P, O. Now this is a functional gene. I just write everything. So what is negative control? Negative control, the first example, if there is some inhibitor attached to the O position, okay, then what happened? This RNA polymerase will not attach to the P. So this will not happen at the beginning. However, there is something coming attached to the inhibitor. Then, to change the morphology, let this guy remove. So what happened? Maybe it looks like this. And then the O, then there's something attached to it. And at this moment, because the inhibitor is not attached to the O, the RNA polymerase and the promoter, they'll get together. They start to attach. Therefore, the transcription happens. At this moment, this effector, we call it inducer. So, this is called negative control of inducible gene. A good example is lacto-operon. Okay, so this is the first thing. This is just a model. Okay, then the second thing what happened is originally this RNA polymerase is combined with promoter. They're very good to start to have a transcription. And then you have an inhibitor right here. Originally is not attached to the O. However, I have some impact there. Once they attach to the inhibitor, this guy gonna go there to attach to the O. Therefore, the transcription stopped. And at this moment, this is called co-repressor. And what is this called? This is called negative control of repressible gene. Remember, when we say negative control, it all happens at O. Now, what is positive control then? Okay, by the way, the negative control repressible gene, tryptophan alpha. Okay, what is positive control? We do the same thing right here. We draw. Okay, we have three locations. Three locations right here. A, P, O, A, P, O, and this is functional gene. So write F here. So what is positive control? Same thing could be inducible and could be repressible. What this means? Originally, this RNA polymerase and the promoter are not connected. And then I have something, this is effector. Is there? And then I have some chemical there, which is inducer there. They combine with the effector, then this guy got attached to the A. Not O, attached to the A. Then RNA polymerase and the P, they combine, they start to have the transcription. So what is it called? This is called positive control of inducible gene. I don't have a good example. A good example, some of you, if you study genetics, maybe Malthus operon. We don't talk about that too much. If I remember, it's Malthus operon. We don't talk about this in here, okay? It's too complicated. Now, what is the positive control of repressible? That means originally, this RNA polymerase is connected with promoter. They are started to do the transcription, 5' to 3'. Now I have an effector right here. It's an effector, let's say. And then I have a co-repressor there. Once they combine together, this whole thing attached to the A, however, this transcription stops. This is called positive control of repressible gene. A good example, I would say Albanose operon. Albanose operon. But we don't want to talk about here, okay? So just give you an example. This is the four basic model we talk about. One is positive control, one is negative control, one is inducible, and one is repressible. Things very twisted your mind. So that's why in this class, we only going to focus on lacto-operon. We don't talk about all the others. Okay, basically in the whole molecular microbiology area or the genetics area, there is three things are really studied very well. Is lacto-operon. Number two is tryptophan operon. And the last one is Albanose operon. Why these are three good examples? Lacto-operon is a very typical example for negative control of inducible gene. Tryptophan is a very good example for negative control of repressible gene. And Albanose is, if you remember, Albanose is like a tunnel, like a bridge. It is a combination of positive and negative control. But lactose is also a combination of positive and negative control. But it's just a touch based. Albanose is a very, very good example of both positive and negative control has been work at the same time. So basically, genetics areas, they talk about those three operon very well. And I believe in biochemistry class, you also talk about the others. But here, we're going to only talk about this lacto-operon. Okay? So, we're going to talk about detail of these things. So we're going to remove these, then we talk about lacto-operon. So this is just the opening remarks, and to help you to understanding basically all these pictures. And that just tells you, if you want to read these are very good to understanding. So we will move on to lacto-operon. So we draw here a basic structure of a lactal operant right here, and then we want to talk about explain something on this side. So lactal operant. First thing first, lactal operant is discovered by two French scientists, Menard and Jacob. This is a Nobel Prize in 1965, if I forgot about it, somewhere between 1960s. Okay, Menard 1910 to 1976, Jacob 1920 to 23. Very long life. And Jacob is Menard students, graduate students, and they work together for the lactal operant. Second, we jump into the basic structure of a lactal operant. Okay, what it looks like. Different textbook could be different, complicated. Genetics book is more complicated. We make it a little bit easy for you. I'm only going to talk about 3 location and 3 location down here, not for others. Here we have CPO. Okay, what are they? C, catabolite activator protein binding site. A little bit of long name. Okay? Now we give them an acronym. CAP, C-A-P. P, easy, promoter. Same thing, later on, RNA polymerase will be there. O, operator. Same thing. Now, in some textbook, between these, there is like a LAC-I inhibitor or something else. We don't talk about that. Just make sure it's COP. And this is, you can write CAP, which is that. Okay? Now, downstream here, there is a 3 functional gene. Is LAC-Z, LAC-Y, and the LAC-X. Some of them say the LAC-A. You can say LAC-X or LAC-A. Okay? What are they? So we are going to write here, okay? LAC-Z, beta, galactosidase. Okay. LAC-Y, beta, lactopermease. Now, LAC-A, lots of the time, we say it is unknown because the function we don't know yet. If you really want to know, it's beta transacetylase. But we don't talk about this one too much because LAC-A, the function is unknown. Before we talk about the lactose operant, you need to know what is lactose. Otherwise, you just remember it. What is lactose? Lactose said very simple. We call it a double sugar. I call it double sugar. It is disaccharides. Okay, how they connected together? What are the 2 sugars become a lactose? There is a 2 different theory. One called the 2 glucose combined together. Another one called the glucose and the lactose. Oh, sorry, and the galactose. So what are they? So let's draw the picture, okay? Let's draw the glucose first. Right here. So we go OH, H, go down, H, OH, OH, H, H, OH, H, CH2, OH. Okay, so we go this side. Usually we do this guy, we get it down. Okay, we can write that like that. This is glucose. Okay, now this side we draw it again. We go H, OH, H, OH, OH, H, H, OH. Sorry, this is OH. H, and then we have H, CH2, OH. What is lactose? This is glucose. This is lactose. What's the difference between that? Regardless of your up and down, for carbon, the hydroxy bond is up and down is different. One is glucose, another one is galactose. Regardless of, okay, one is up, one is down. Then what is lactose? That is lactose. This is lactose. The whole thing. So it's a double sugar. What is this bond name? 1' 4' glycosidic bonds. We know that lactose, if in the body we use, you need to have galactose, or you need to have beta glycosidase. Is that right? You need to have beta glycosidase. Beta glycosidase will become what? Galactosidase. Obviously, will hydrolyze become glucose and lactose. Is that right? Since they are also combined, if you have a beta glycosidase, will break them. Some people do not have beta glycosidase in your intestinal areas. Then what is going to happen? Lactose intolerance. So basically, an obvious phenomenon is you cannot drink milk. If you drink milk, you have a diarrhea, abdomen pain, sometimes vomiting even. Not really vomiting, but diarrhea you're going to have. Lactose intolerance. So we call lactose intolerance. Okay, what are we going to do then? People cannot drink liquid milk. What do we have to do? They can buy drink powder, milk powder, is that right? Because the milk powder, they freeze drying and then they later on add beta glycosidase. So you don't have it, but the products have it, so will be hydrolyzed, become galactose and glucose. So this is the first thing you need to know, okay? Second thing, in the bacteria, when the lactose become beta glycosidase, become galactose and glucose based on the function of the glycosidase, they also will have a side reaction. This is called a side reaction. What is a side reaction? Instead of you have a 1,4 glycosidic bonds, I have a 1,6 glycosidic bonds. So what does it look like? We have to draw it again. Right here. OH, H, H, OH, OH, H, and we go down. OH, H, H, CH2, O, right there. Okay, now we're going to draw it again right here. Okay. What happened is OH, H, H, OH, OH, H. This OH is up. H, H, CH2, OH. Now what's going to be? This goes here. That is 1 prime, 2 prime, 3 prime, 4 prime, 5 prime, and 6 prime. And this is 1 prime. So what is that? That is 1 prime, 6 prime, glycosidic bond. What is this product? Allolactose. This is the key right here. Okay. Now let's think about it in your mind. This is a huge bacterial cell, like this. How bacteria come in? How lactose come in? They need to dig a hole. There's a channel let them come in. Okay, lactose coming from outside of the bacterial cell. Go to the channel, go inside of the cell membrane system. They need an enzyme. It's permease. They need beta lactopermease. What is permease? Permit. Okay, when you're parking somewhere, you need to have a permit. Otherwise, you get a ticket. When you go to see the museum or like the show or some of the football game, you need a permit. Basically, it's a ticket. You go inside. So that is what permease in penetrate. Permit, you come in. Now, by the way, when you see here ASE, which means it's an enzyme, is that right? So these two we explained. So this is what happened. A basic reaction you need to know. Lactose come in based on beta lactopermease. They come in. If the bacterial cell have beta galactose, what happened? Lactose will be break down, become galactose and glucose. At the same time, there's a side reaction will generate a minimal or a lower level allolactose. More or less, it will be there. So therefore, it comes out with the theory, with the lacto-operon. Okay, so let's do it again. Lacto-operon, we have cap, P, and O. This is lac Z, lac Y, and the lac A. And I have another one here, right here, okay? We draw it again. When you draw a couple of times, these things are easy to understand. We have a cap, the P, O, lac Z, lac Y, and the lac A. So what happened? At the beginning, when they do not have a lactose, there is an inhibitor, which is right here, attached to the O. What is that? It is a tetramer. How they attach to the O? There is a two function. This is the O, let's say. We have O1 and O3. We twist it. Then the tetramer will be attached to it like this. And what happened is this tetramer could also attach to O1 and O2. That will be attached like this. Now why they can do it? Because the secondary structure of this tetramer is helixy, turn, and helixy. It's a secondary structure of the tetramer. So originally, like that, they attach to the O. When they attach to the operator, this RNA polymerase is not attached to the promoter. They are not combined. So there is no transcription happening, which means there's no lag Z, no lag Y, and no lag A. Okay? This 5' to 3' transcription, they stop. Now, if there is a lactose, what's going to happen? When the lactose comes in, the allolactose will be generated. So what happens? This allolactose will be go there. Once the allolactose goes there, they change the morphology. So this one will change the morphology. They may change a little bit. This allolactose goes here. They will be let the tetramer not combine to O. They will release. Okay, then what happened? Then the RNA polymerase will attach to the promoter, and then the transcription will happen. That's 5' to 3'. Therefore, the lag Z started to transcript, the lag Y started to transcript, then more and more lactose could come in, then lactose will break down, become galactose and glucose. Then bacteria can use it. Then they can go ahead to survive. At this moment, we say this allolactose is an inducer. This whole thing is a negative control of inducible gene. And don't forget this phenomenon. Allolactose, when they come in, change the morphology of the tetramer. So that the tetramer is not attached to the O. What is the name for this? Allosteric reaction. This is one of the methods to inhibit enzyme function. So we call it a non-competitive inhibition. Is that right? We mentioned about that. I said I'm going to explain to you when we talk about lacto operant. What is the competitive inhibition? PABA and the sulfur drug. Sulfur drugs, the morphology is very same as the PABA, so they will grab the place of originally should be PABAs, and the bacteria will not synthesize folic acids, so they will be died. Because folic acid has to be absorbed from the external food resource. So this is something we finished talk at this moment. Okay, when Menard and Jacob, when they find this, they publish the paper, they win the Nobel Prize, and they are happy that they go to celebrate. Remember, Watson and Crick, how they celebrate, they go to an Eagle pub, buy the beer for everybody, but although nobody knows what's going on. They do the same thing. But later on, people find it's not complete. Why? We haven't talked about this guy yet. Is it right? There's nothing happened on the cap. I spent it so many times talking about, draw so many pictures. How about the cap area? There's nothing happening yet. So, people start to do more research to find the cap area, what's going on there. And very occasionally, the research is done when they do the bacteria survival curves. So this is what happens. Okay, we had a bacterial media. This is time. This is a number. In this bacterial media, we have glucose. Then we add lactose. What happened? I grow E. coli there. A very simple E. coli strain. What happened? They find the growth curve is like this. They're like that. So it looks like there's a double growth there. Remember, if you forgot about it, what is the growth curve? Remember exam 1? We talk about the standard growth curve, lag phase, log phase, stationary phase, and death phase. That's a normal. This is time. Y-axis is number, population. That looks like that. Then how come I grow E. coli in glucose and the lactose? It's like a double growth there. This is called dioxic growth. What happened? That tells you when in the environment there is a glucose and the lactose, bacteria favorable to use one of them first, then do the other. Is that right? Very obvious. If they use them together, you want to have a second curve. So then they do isolation. Later on they find they do use glucose first. And then they start to use lactose. And I will say this is a very smart and economic way for bacteria to survive. This is a lactose combined with galactose and glucose. It's a double sugar disaccharides. Glucose is a monosaccharide. So for bacteria, in the co-presence of monosaccharides and the disaccharides, they will use monosaccharides first. Then they start to use glucose. But then they start to use disaccharides, which is lactose. Now, obviously, lactose is still breakdown. It makes sense, is that right? When you go Halloween party, you say you're going to buy a pumpkin. The pumpkin is $5. In your pocket, there's a $5 bill is a glucose, and $10 bill is a lactose. What you use first? Of course you use a $5 bill, is that right? It's easy, just $5 bill. Unless you want to show off, you give somebody $100, said I want some change, to show people you're very rich. If that makes sense, you have a $5 bill like glucose, and $10 bill like a lactose. We use a $5 bill first. So same thing for the bacteria. Okay, when this one happened, then they start to think about, how come this is the phenomenon happens, there's a double growth. Then later on to do the research, people do lots of research, okay, on and on. What they find, that's related to the cap. And this area, you have to combine with CAMP. Then they will start to work. And the CAMP, combined to the cap, we call it a positive control. And at the same time, the inducible has to be attached to tetramer to do the same thing. Which means they have to work very well. So, people start to realize lactose operon is not that easy. It's not only negative control. It is a combination of positive and negative control. Then they start to see more research about CMP, what it is. Now, we want to talk about something we studied before. Okay, I don't know whether we have a space here, but we will talk about it. So what it is? Remember, we talked about this. This is a bacterial cell membrane system. Like that. Okay. You have these lipids, which is hydrophilic head, hydrophobic tail. And then you have these complex right there, like enzyme 2, some complex there. Okay? Then, bacteria going through the process. Okay, when we use a glucose, let's say there's a glucose in the media, okay? What they become? Glucose 6-phosphate. We're gonna draw it, okay? Fructose 6-phosphate, because there's something we have to explain to you. Then go down. That's called glycolysis. We mentioned about fructose 1,6,5-phosphate. Then we go to channel right here. Glycerol behind 3 phosphates. 1,3,5-phosphoglycerate. Okay, 3-phosphoglycerate. These are easy ones. Okay, 2-phosphoglycerate. Okay, it's gonna be the key. Phosphoenolpyruvate. And the final product is pyruvate. remember, when I talk about the glycolysis at the beginning, I asked you, what is the enzyme for this one? Lots of you tell me, hexokinase, is that right? That's what you learned in your biochemistry class. So I said for bacteria is not. Is what? Group translocation. Group translocation requiring this guy, phosphoenolpyruvate. What's the acronym? PEP. Go back to review exam 1. You pretty much forgot about it. So what happened? PEP is right here. So you're going to go into enzyme 1. So you're going to go into HRP, heat stable protein. Then the phosphate will be transferred. Remember, the phosphate will be transferred. Okay, the phosphate is going to go here. And I said, if there is a glucose there, what's going to happen? This glucose will go inside of the cell membrane system, become glucose 6-phosphate. This is right there. You know the reason why I want to draw this. Draw this, okay? If there is a glucose, what happens? There is PEP there. Is that right? Phosphoenolpyruvate. So you will do this transfer from enzyme 1, heat stable protein, enzyme 2 complex. Then the glucose will be receive the phosphate donated from PEP, become glucose 6-phosphate. It will start to jump in to do the glycolysis. How about if there is no glucose? If this guy is gone, what happens? They're still doing this. Instead of they become glucose 6-phosphate, they're going to activate something here, which is called AC. What is that?